These are the notes for AP Calculus on integration. So integration, if you just think about the meaning of the word in English, means kind of putting things together, is the reverse of the word differentiation, means to kind of separate things. And integration itself is the reverse of differentiation. So it's the process of finding what's called the antiderivative, or sometimes referred to as the indefinite integral. The symbol we use for integration looks like this. So when you see this symbol, it means you're integrating whatever's to the right of that. And it's always followed at the very end of the integration. What's called the integrand is inside the integral there is followed by the differential. Usually dx, dy, d theta, dt, or it could really be d any variable. And we'll see some meanings of the differential a little bit more later on, but just think this is an infinitesimally small change in that variable. And it indicates, for now, the main purpose of it is going to be to indicate the variable of the integral, so you know what variable to use. So let's start with what you've already learned, and that's how to find the derivative, and then try to reverse that process. So if we had y equals x squared minus 4x, and you took the derivative, then the derivative of y, that'd be dy dx, equals the derivative of x squared, it's 2x, then minus the derivative of 4x, it's negative 4. And so one way of thinking about integration or finding the antiderivative, let's say we started with this as the derivative, and we're trying to get back to the original equation. Let's say we didn't know what that original equation was. Well, the first thing technically you have to do before you can integrate it is what's called separating the variables. In other words, all the x terms have to be on the side with dx, and all the terms, if there were any y terms, would have to be with dy. So the way you can separate the dy from the dx is to multiply both sides of the equation by dx. And that'll leave you with dy, since the dx is reduced out there, equals 2x minus 4 times dx. So now the variables are separated. X is with the dx, and if there were any y terms, again, they'd have to be here with the dy. And then that allows us, what we can do is integrate both sides. We use the integral symbol. And then to integrate the dy, well, what's really in front of the dy, even though it's not written there, is a 1, right? And let's first, before we look at the rules for antiderivatives for basic integrals, let's think about in reverse. What would give you a derivative of 1? Well, that'd be x. But in this case, the y tells us the variable is not x, it's y. So this would be y. Equals, well, think, what gives you a derivative of 2x? Well, that would be x squared, right? And what gives you a derivative of negative 4? That would be negative 4x. So those would be the antiderivatives of those terms. You might think that's it. That gives us back our original equation. However, there's one more thing we have to account for. What if, for instance, there was a constant after the 4x, let's say of plus 3? Well, would the derivative have changed at all? No, because the derivative of a constant by itself is just 0, right? So that could have been negative 3, it could have been negative 3, it could have been negative 7, it could have been 0, it could be negative pi. Any constant would have had the derivative of 0. So when you're finding the antiderivative, you have to account for that unknown constant. It didn't have to be 0, it could be any of these, and we'd have the same derivative. So we do that by putting a plus capital C to represent that constant. And that's one reason why it's called an indefinite integral. You don't have a definite answer because of that unknown constant unless you're given more information. All right, so now let's take a look at the basic rules for integration. So if you're integrating a constant here, k also represents a constant. And capital C is a constant as well. Okay. Well, all that happens is that constant gets multiplied by the variable, which in this case, dx tells you the variable is x. And then you have that unknown constant plus c. So an example of that would be 5. When you integrate 5, the dx tells you, well, that's just going to become 5x. Just think, because the derivative of 5x gives you back 5, right? So the antiderivative of 5 is 5x. And then again, there's some unknown constant plus c. And then the reverse of the power rule, think about, let's slow down how the power rule works. Let's say we had x to the 5th, for instance. And we were taking the derivative of that. Well, you'd bring down the 5, and then you'd reduce the exponent by 1, right? Subtract 1 from it, so it becomes 5x to the 4th. Well, if we're going to integrate, look at what happens. The power rule for integration, you add 1 to the add exponent. That reverses the subtracting 1 from the exponent. And then you divide by that exponent. That reverses the multiplying by the exponent. So let's see how that works for x to the 4th. Well, first you'd add 1 to the exponent, so that would become x to the 5th. And then you divide by that exponent, which is 5. And then we need our unknown constant plus c. The nice thing on a lot of these that are real simple like this, you can easily check your answer to see if the antiderivative is right by just taking the derivative of what you get. So if we took the derivative of this, you'd bring down the 5, the 5s would cancel out, and you'd have x to the 4th, and the derivative of the constant would be 0. So you can see this would be the correct antiderivative. However, for derivatives, that works for any exponent. For antiderivatives or integrals, it works for any exponent except for -1. So let's see why it wouldn't work for -1. So if we had the integral of x to the -1 times dx, well, if you add 1 to that exponent, that's going to become x to the 0. And that means you'd have to divide by 0, and that's undefined. We divide by 0. So that's why it doesn't work for 0. There is a way to find the antiderivative x to the -1, but it requires something else that we'll go into later on. So for now, we won't deal with that. But it works for any exponent other than -1. All right, now let's look at some other rules that are very similar to the derivative rules for the antiderivative. This just says if you have a constant k out in front, you can actually pull it outside of the integral. We'll see sometimes that's actually helpful. It makes it easier to simplify. So on this one, you can actually pull this constant of -2 outside the integral, because just like with derivatives, a constant out in front just stays there. And then you would have x cubed times dx. And then when you integrate x to the 3rd using the power rule, that would give you x to the 4th. So -2 would just get multiplied. Add 1 to the exponent divided by 4, and then plus some unknown constant c. And then we can simplify that. 2 goes into 4 twice. So that would reduce to be -x to the 4th over 2, and then plus some unknown constant c. All right, and then remember when you have terms added or subtracted when you're integrating, you can integrate each one separately, just like with derivatives. So we actually could split this up into the integral of x to the 5th times dx plus the integral of x times dx. Notice when you split it up, they both need to have dx. So it's kind of like you're distributing the dx out to both of them. And then when you integrate x to the 5th, that would give you x to the 6th, add 1 to it, divided by 6 using the power rule for integration. Now you could have a plus c here. However, this one's also going to have a plus an unknown constant. So those two unknown constants, there's not really a need to have two different ones, when really you could combine those two to just be one unknown constant at the very end. So when you integrate x, that's like x to the 1st, add 1 to the exponent, x squared divided by 2, and then plus some unknown constant c. All right, let's take a look at a few more examples. Next two say find the general solution of the differential equation and check the result by differentiation. Okay. So when it says the general solution, it's because there's going to be a plus c in our answer. We're not going to know what that c is. And what we're going to solve for, basically we're starting with a derivative on both of these. We're trying to get back to the original equation. That's what it means by the solution. So we're going to solve for whatever variable is on the numerator of your derivative. In this case, it's a y. In this case, it's r. So the first thing technically we have to do before we can integrate is separate the variables by multiplying, in this case, both sides by dx. So then we'll have dy equals 5x to the 2/3 times dx. Now the variables are separated. X is with the dx. If there were any y's, they'd be with dy. Now we can integrate both sides. And again, in front of the dy, we really have a 1. So that's the constant rule. It's multiplied by the variable, which is y. So you integrate that, that gives you y. Now, technically, we would have a plus c here. But same idea. If we've got two different integrals, if we have an unknown constant on the left side and an unknown constant on the right side, you can really combine those on one side to just be one unknown constant. You could really put it on either side, but remember we're going to try to solve for y. So it's probably actually easier to have it on the right side to start with to make that y easier to isolate. So this way it's already isolated. And then when you integrate 5x to the 2/3, again the 5 just stays out in front. If you want, you could pull it outside the integral, but you don't have to. We'll see later on where that's more useful. And then this is the first fractional exponent we've run into, but you can still use the power rule as long as it's not a -1. So when you add 1 to that, think that's going to be really like adding 3/3. So 2/3 plus 3/3, that would give you x to the 5/3. Remember, then you have to divide by that exponent. But instead of dividing by 5/3, which looks a little more complicated than it really needs to be, just remember the rule for dividing fractions. Dividing by a fraction is the same, remember, as multiplying by the reciprocal, which is 3/5. And then you have some plus some unknown constants. And then we can simplify that. You can see the 5's reduce out. And we have y equals 3x to the 5/3 plus c. And then we can switch it back to radical form. So it would be y equals 3. It would be the cube root of x to the 5th plus c. So that would be the general solution. The original equation that has this as the derivative. Now to check your answer, check the result by differentiation, you can start with either form here, but it's probably easier to start with this form. It's not in radical form. And we could say, well, the derivative of y, that would be dy dx. Use the power rule 3/5 times 3. Well, the 3's are going to cancel out, leaving you with 5. Subtract 1 from the exponent, gives you x to the 2/3. Derivative of constant is 0. So it does work. Now let's try the next one. This time we have to separate the r and the t as our first step by multiplying both sides by dt. So you get dr equals 2t to the -4th times dt. Again, the t's now with the dt. If there were any r's, it'd be over here on the side with the dr. And then that allows us to integrate both sides. Again, what's in front of the dr is a 1. So when you integrate that using the constant, it just gets multiplied by the variable, which in this case is r instead of y. So it's r equals. And we've got 2. When you use the power on that, that would be t to the -3. Add 1 to the exponent, divide by that exponent -3, and then plus some unknown constant c. And if we simplify it, that would be 2 over -3. Bring the negative exponent down below, so it would be t to the 3rd plus c. So there's our general solution. We've solved it for r. And then to check your result by differentiation, it's probably easier to use this form with a negative exponent, because in this form you'd have to use the quotient rule. So if we check using this form, notice using the power rule, this is like a -2/3 out in front. Your derivative would be written dr dt this time. The -3, when we bring it down, would cancel out this -3, leaving you with just 2. T to the subtract 1 from the exponent, -4. And the derivative of a constant is 0, so it does work out to be the same as our original problem. All right, now let's look at some that are not in the form of an equation where it's written as a derivative. We're just actually getting some practice when the integral symbol is already there. It says evaluate the indefinite integral. And do not leave any negative or fractional exponents. So this is just getting some practice applying the rules before later on we'll see some applications of integration. Okay, so with integration, there is no product rule. There's something called integration by parts, which we'll see later on, that derives from the product rule for derivatives, but there's not a product rule itself for integration. So since these are multiplied together, there's not a product rule we can use, so we just have to multiply it out. So you get 2x to the 4th minus 7x cubed plus 3x squared plus 4x. And now, remember, we can integrate each of these separately since they're just added and subtracted. So the constant 2 stays out in front. Then you add 1 to the exponent, so it'll be x to the 5th over 5 minus 7. Then add 1 to the exponent, x to the 4th over 4 plus 3x to the 3rd over 3 plus 4. This is like x to the 1st, so it becomes x squared over 2. And then plus an unknown constant c. So we're just applying the power rule on each one of those. And let's see if any of them simplify here. Well, in this one, the 3's reduce out, and here 4 divided by 2 is 2. So our simplified answer would be 2x to the 5th over 5 minus 7x to the 4th over 4 plus x cubed plus 2x squared plus c. On these, if you want to check your answer, you can by taking the derivative, but you don't have to. All right, let's take a look at a few more. All right, on this one, remember with derivatives, anytime you had something in radical form, we always rewrote it with fractional exponents to make it easier to apply the power rule. The same thing is true of antiderivatives when you're finding the integral. So let's rewrite this. So the integral symbol stays there. Notice one thing I didn't point out, but you may have or may not have noticed, is once you've integrated, this integral symbol and the dx go away. But they remain there until you've integrated. This reminds you still have to integrate this, and the dx reminds you what the variable is. So when you rewrite this, if we still haven't integrated, we'll leave the integral symbol there. X squared of x is the same as x to the 1/2 plus the cube root of x squared is the same as x to the 2/3 minus, here we can just pull that 1/3 out in front, negative 1/3. And since it's x to the 1/2, but it's on the denominator, if we move it up, it becomes x to the negative 1/2. And this one, there's also no quotient rule for integration. So we have to rewrite that as 2x to the negative 3. All right, now we can apply the power rule to each one of these. So we'd add 1 to the exponent. That's like adding 2 halves. 1/2 plus 2 halves is 3 halves. But again, remember when you have a fraction, instead of dividing by 3 halves, that's the same as multiplying by the reciprocal 2/3. Plus x to the, when you add 3/3 to 2/3, that gives you 5/3. Divided by 5/3, the same as multiplying by 3/5. Minus 1/3 stays out in front. When you add 1 to negative 1/2, that's like adding 2 halves. That gives you a positive 1/2. Dividing by 1/2 is like multiplying by the reciprocal 2. Plus 2x to the negative 2 when you add 1 to that exponent, divided by negative 2, plus our unknown constant c. Remember, we're not going to leave any negative or fractional exponents, so our last step to simplify this. This would be 2, and then in radical form, it would be the square root of x cubed over 3, plus 3. This would be the cube root of x to the 5th over 5, minus 2 square root of x over 3. And here the 2's reduce out, so you're left with the negative, and that x to the negative 2 can be written as 1 over x squared plus c. Okay, let's take a look at a couple more. On this next one, again, there's no quotient rule for integration, so we can use a strategy I also showed you guys for derivatives. When you have a single monomial on the denominator, one strategy you can use so you can avoid the quotient rule on derivatives, but here there is no quotient rule, so we have to use it to rewrite this, is to split up the fraction. Divide them all by that monomial denominator. So we have 3x to the 4th over x cubed plus 2x cubed over x cubed minus x over x cubed plus 4 over x cubed. We still haven't integrated, so the integral symbol and the dx still stay there. And we still haven't integrated. Let's simplify this. That's going to be 3x. Here the x cubes cancel out, plus 2 minus, could write it as 1 over x squared, but to make it easier to integrate, that would be x to the negative 2. And instead of 4 over x cubed, again use negative exponents, 4x to the negative 3. Now we can integrate each one separately, so they're just added and subtracted. So the 3 would stay there. Remember, this is x to the 1st, so it becomes x squared over 2 plus 2. Now it's a constant. When you integrate antiderivative, you just multiply it by the variable 2x, because the derivative of 2x would be 2. Then minus, when you integrate that, add 1 to it, it gives you x to the negative 1 divided by negative 1 plus 4x to the, add 1 to it, negative 2 divided by negative 2. and then plus c. All right, and let's simplify what we can. No negative or fractional exponents, so first two terms are simple. They're just going to get 3x squared over 2 plus 2x. Here the negatives cancel out, so it's plus. Instead of x to the negative 1, that's 1 over x. Here 4 divided by negative 2 is negative 2, and then over x squared, and then plus c. All right, let's take a look at one more. Again, no product rule for integration. This one kind of looks like if you're taking the derivative, you use the chain rule. And there's something we'll go over in just a little bit on the chain rule. For integration, it has a different name, but it's similar to the chain rule. It's when you have a function inside. But that would actually wouldn't work on this one. It's a little too complicated. So there's no product rule. So let's just go ahead and rewrite this. Since it's squared, it's 2 square root of t minus 3t times another 2 square root of t minus 3t. And let's just multiply it out so that we don't need the product, because there is no product rule for integration. So we still have an integrate, so we leave the integral sign there. 2 square root of t times 2 square root of t. Well, 2 times 2 is 4, and the square root of t times the square root of t gives you t. Then 2 square root of t times negative 3t gives you negative 6 t squared root of t. And then the same thing here, you get another negative 6 t squared root of t. And then you get positive 9 t squared. But these middle terms, there's no product rule, so t squared root of t, let's figure out how else we could write that. Well, another way of writing this is like t to the first, and this is like t to the 1/2, right? And this is another negative 6t to the first, t to the 1/2. And if you multiply those together, remember you add the exponents. So that'd be negative 6t to the 3/2. That's 2/2 plus 1/2, minus another 6t to the 3/2. So when you combine those before we integrate, it's going to be 4t minus 12t to the 3/2, and then plus 9t squared. All right, now let's go ahead and integrate each one of these. So integrate 4t, 4 stays there, you get t squared over 2, minus 12 stays there, you get t when you add 1 to that. Back adding 2/2 gives you 5/2, times the reciprocal 2/5, instead of divided by 5/2, plus 9t cubed over 3, plus c. And finally, let's simplify and get rid of any negative exponents. So here the 4 divided by 2 is just 2, so that's 2t squared. And then minus 24, and in radical form, that's the square root of t to the 5th over 5. Plus here, 9 divided by 3 is 3, so 3t cubed plus c. And that concludes the notes for AP Calculus on the topic of basic integration rules.